So welcome to everyone who is joining us from the recording. I need to get into the right section, which for this week was 2.8. We just covered one section this week, which is related rates. So the gist of this is we have something that is happening, right? And it's reliant on something else that is happening, usually with changing over time. And we need to find out a way to relate these two processes to one another. And it's usually fairly straightforward. Like, we can go ahead and start. This is section 2.8. I am on page 185 right now. And I believe this is section 3.9 in the other version of the book.
Okay, good.
And so I have just like question one, like what's up here? We have the volume of a cube with an edge length x, and the cube is expanding over time. So there are kind of like steps to these kind of problems.
Sure.
It's good to draw out what's happening. Let's see if I remember how to draw a cube. Something like this.
Yeah.
That's kind of like falling in on itself, but we kind of get the gist of it.
Sure.
Where we have side lengths that are all x. So they're all going to be changing at the same rate. So what would the equation for the volume of this cube be? Exactly.
For the volume of the cube. Sure.
So volume is going to be equal to length times width times height. And if that is equal to x, and that is equal to x, and that is equal to x, then it's going to be this equation. So if the cube expands as time passes, then we really have this equation. The volume is equal to this function x of t, and x of t is to the third. So it's asking us to find dv dt in terms of dx dt. So this is what we want. Another thing that is really handy when you do these problems, in addition to drawing, is to very explicitly label like what you have and what you want. Yeah. So this is what I have right there. And this is what I want. So how am I going to get from what I have to what I want?
So we have the we have the equation of the volume of the cube. We don't know yet what the either of the rates are. Correct? Like we don't know the rate of the volume as time changes, and we don't know the rate of the side as time changes, do we?
No. We're basically trying to find an equation that relates the two of them. So we want an equation where we can use to determine that. So yeah.
Okay. Yeah. I'm looking at what Hayden's saying. We take the derivative of the equation for volume.
Yeah.
Correct.
So what we're going to do basically is pretend we had this function that is v of x, right? And it is x cubed. It would be really easy to find v prime of x, which would be 3x squared. However, what we need to recognize is that x is actually x of t. So all of this is dependent on time. And this would be dv dx. Yeah, so what we need to do is we need to build this as if we were solving a problem with the chain rule, in that we have an equation that is v of x of t is equal to x of t cubed And so we need to, if we were to take the derivative with respect to t, so d dt, we're going to end up with dv, and this is implicitly, right? I'm taking this implicit derivative.
Mm-hmm.
So I'll end up with dv dt is equal to dv dx times dx dt. Because this is a chain rule, I can say that I have, if you remember when we were doing the chain rule, we would have a function that looked like this, where v is equal to like x cubed, or here, I'll rewrite this in a little bit of a different way. I'm trying to like
a substitution, you mean?
Basically, yeah.
Okay.
So we would say that we have this function v, right? And v is a function of x, and that is equal to x cubed. So v prime would be equal to 3x squared, and then x is equal to x of t. And so x of t prime is equal to dx dt. And we don't need to get any more specific than this, because we don't need to know what x is, as like, we don't need a function that defines x without it we don't need a function that defines x, because we know that we're looking for the derivative of x. So basically
Sure.
what I just said here is that the derivative of x is equal to the derivative of x.
Right.
And x is equal to x, and that's fine. But the reason I'm doing this is because I want to put it into language that we've used before.
Sure.
So if I had this function v of x of t, and I wanted to take its derivative, I would end up with something that was of the form v prime of x times x prime. In this case, dv dx dx dt. Right? Because this is v prime of x, this is dx dt.
Yes.
Okay.
Sorry, there's noise happening in the background.
You're good. So we're all cool with how we got here via chain rule. Okay. So now we, as established earlier, dv dx. Oh, that's not the right green. That was a very ugly green. Dv dx is equal to 3x squared, and dx dt is equal to dx dt. So dv dt is equal to 3x squared dx dt. And that is our equation here. So, and that's all we needed to do with this problem, because all they wanted us to do was write dv dt in terms of dx dt.
Right.
How can I use this is like the next kind of question. And the only way that I can really use this is, I've got 3 different variables going on right now. I've got a rate of change of volume. I've got a rate of change of the side length.
Mm-hmm.
And then I've got a side length. Right? So these types of problems will give you 2 out of the 3, or make it like possible for you to determine 2 out of these 3. In that it'll say the side length is changing at a constant rate of 3 meters per second. And the side, they want you to find the volume when the side length is 2.5 meters long, right? So they will give you like pieces of this in the problem. And if you don't have all of that, if you think you have an equation but you're missing something, you're either missing a part of the problem or your equation isn't quite right. Sure. So it's oftentimes like a struggle to determine exactly what's missing and when. And that's why this section is a standalone. Because
sure.
This and optimization are kind of, which I mean we'll get to later, is just kind of like a large stress for people because it's a lot of figuring out exactly what's going on. Okay, let's do problem 3, which is very similar to problem 1, and I believe it's the same in both books. It should be, I think it is. So we have a square, and so each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So, first things first, what do I have and what do I want?
Well, so there's kind of like something nested in here I found out. We have the area of the square, which we can use to figure out what the side of the square is. So it's kind of like it gives us part of what we have, which is just side times side. So square root of 16.4. I think you wrote that.
Okay. What else do we have?
We have the rate. We have the rate of change of the side, or one or both.
What do I want?
What we want is the rate of change of the area of the square.
Okay, so the next step is to put this in terms of math.
Sure.
What do I want in terms, like using like math lingo?
You mean like actually setting up the equation?
Sort of, yeah.
Okay.
We don't need to set up the equation though to say what I want. Because what I want is the derivative of A with respect to t, right? The rate of change of the area with respect to time, which I can write pretty easily as dA dt. And so we know what kind of a problem we're going to be setting up. And then what can I turn this rate of change of the sides into? What is this equal to in like math lingo?
I'm not I'm not entirely sure the context of the question.
Yeah, so anytime you see rate of change, think the word derivative.
Oh, right. Yeah, okay. I'm sorry. I was there, just I wasn't sure of how the question was being phrased.
Fine. I'm sorry.
So, no, that's cool. It was kind of there. But yes, like Hayden was saying, we can set what we want, the d of a over d of t equal to the side squared times the rate of change of the side. I don't know if that was
that wasn't quite the question. That's a little bit far ahead.
I'm sorry. I'm jumping over something.
No, it's good. I was literally just going for it's the derivative. So it's the change in x with respect to time.
Got it.
So if you like say it out like that every time, like the derivative of the length of the side, which is x with respect to time, then you can build yourself something in Leibniz notation really easily.
Got it.
So now let's set up an equation. What is the equation for the area of the square with side length x?
Oh, just side squared.
And what is going to happen if I differentiate implicitly with respect to t?
Just 2x.
And?
Times dx over dt.
Dx dt. precisely.
Right.
So now I have, this is x, this is dx dt, and I want dA dt. I have 3 different variables. I'm given 2 of them. So I can go ahead and put this together. dA dt will be equal to 2 times x, which is 4 centimeters, times dx dt, which is 6 meters per second, or centimeters per second. Centimeters per second. So this will be 2448. And I put the units in here because the units should all turn out and make sense. So this will be centimeters squared per second is equal to dA dt. Does this make sense as an answer?
Yes.
Yep, because area is going to be measured in centimeters squared, and time, we're measuring it in seconds. So a change, the rate of change is in centimeters per second, and that makes sense.
Yeah.
Okay. Let's try to do number 13. And I think they're the same. They should be the same.
A plane flying horizontally?
Yes.
Okay.
So we have a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour. It passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So we're going to draw.
Yeah. I usually find that being that's usually how I started these when I was doing.
So I'm just gonna call this my plane. That's a beautiful plane.
Yeah.
And this is gonna be my radar station. And I have a vertical distance and a horizontal distance from my radar station, right?
Mm-hmm.
And then I have the actual distance from the radar station.
Yep.
So, shoot. So yeah, so I basically have this triangle set up.
The plane went away.
Sorry. All right, so let's fill in what I can right here. Which of these is like constant? Like which of these values is known for certain and isn't changing over the course of this problem?
The height of the plane over the radar.
Yes. So this
station.
height, we'll call it y, which is equal to 1 mile. What else do I know?
We know that the plane is flying 500 miles an hour.
Okay. What else do I have?
We have, I guess part of what we want to find is when it is 2 miles from the station.
And is that actual distance or horizontal distance?
It says 2 miles away. Well, I mean, I guess it doesn't say, but my implication was the horizontal distance. Is that not? I mean, I don't think it's.
That's also what I was thinking, and now I'm reading this again, and I'm second guessing myself.
Well, it doesn't. Well, see, I figured because the speed is measured horizontally, not between the actual distance from the plane to the radar tower. So if it's flying 500 miles an hour, 2 miles in the direction that it's flying from the height of the radar station. That's how I think I at least did the problem, and I think that's what yielded the correct answer was using that value?
Well, let's keep solving and then we'll find out. 2 miles
Okay.
from, we'll figure it out at a later time. We'll postpone this problem.
Okay.
Not like the whole problem, but like this
Sure.
specific issue.
Got it.
And see if it kind of elucidates itself as we continue. So 2 miles from the station, and we also have the altitude, which is 1 mile up. So y is equal to 1 mile. Okay, so let's go ahead and figure out what we need. What is it exactly that we want?
So we want to find the rate the distance is increasing. So I guess depending on what variable we set that
Okay.
side
This is
to.
for certain going to be this rate of change.
Okay.
So if we call this z,
All right.
then this is going to be the rate of change of distance from the station, or dz dt.
Yep.
Okay. So now, so we did part A, which is what are the quantities given. We did part B, which is what is the unknown. We already did part C, which is draw a picture at any time t. So now we need to write an equation that relates these quantities. So what kind of an equation do you think that we should write?
So when I did this, I usually started with the Pythagorean Theorem to get all three sides, which would then help us find dz of dt.
So let's call this x. So Pythagorean Theorem, we have y squared plus x squared is equal to z squared. We know that y is equal to 1, so y squared is equal to 1.
Sure.
So I can go ahead and say this is 1 plus x squared is equal to z squared. So yeah, this is our equation that relates the two. Let's just go ahead and differentiate. So we have the derivative of 1 with respect to t, the derivative of x squared with respect to t, and the derivative of z squared with respect to t. So what is this going to turn out to be?
So derivative of 1 is going to be 0. And then we'll be left with 2x equals 2z.
2x?
I'm sorry. 2x dx dt equals 2z dz dt.
Yeah, it's always really important to remember that when you're implicitly differentiating.
Yes.
Yeah. This is like also something that I struggled with, but like that's just like a vital part of what's happening here.
Sure. Yeah. Well, I mean, that's like, I feel like that's like the whole rate aspect of it. Yeah.
Okay. So now we have this equation that relates not only that relates both like x and z and dx dt and d dt. Okay. So now we need to finish solving the problem in part E. So how are we going to finish solving this problem?
I feel like now's the time when we need to decide if we're setting 2 miles as well, basically x or z.
Yeah. I'm pretty... Well, feel like it should be x, right?
That's like when I did like I said, when I did this on a WebAssign, like I'm 99% sure that that's I mean I don't know if they worded the question differently, but the question that was set up just like this, I used X for it, and
Okay.
I believe that yielded the correct answer. I mean, I don't know if there's the answers to this in the back or something, but I'm sure we can compare
Okay.
it.
Yeah, I actually just opened that up right now.
Okay.
And it
Chapter.
seems to be implying that when x is equal to it sets up when z is equal to 2.
Oh, really? Okay.
Yeah.
I mean, I
So,
guess I
yeah.
mean, essentially, we'll be doing this
Yeah.
the
Okay.
process the same, just different.
Yeah. So it's the same process.
Okay.
If we were, I think they usually are pretty decent about explicitly stating like the horizontal distance versus the distance.
Yeah, I guess
So it's,
the distance would be
yeah.
z. All right.
Okay, so now we have established we have the distance, so this is going to be equal to z.
Got it.
How are we going to find the rest of this?
Well, so if z is 2, we can plug 2 in for z.
Exactly. So we have z squared, which is 2 squared, plus x, or excuse me, is equal to x squared plus 1. So 4 minus 1, x squared. So x is going to be equal to plus or minus the square root of 3. And because we don't want to have negative length, it's just going to be the square root of 3.
Right.
That's one of the good things about having this type of problem.
Yes, I did enjoy that part. It's like I don't have to like do 2 different answers.
Okay, so we now know that x is equal to the square root of 3. We have z, which we said is 2 miles. So what else do we have that we haven't labeled in terms of math yet?
We do have the rate of change of, or we have dx of dt.
Yes. So this is the change in horizontal. So that's dx dt.
Yeah.
So we can start plugging stuff in. 2 times x, which is the square root of 3. And this is in what units?
Miles?
Mm-hmm.
Okay.
Miles. And then dx dt is 500 miles per hour. And that's equal to 2 times z, which is going to be 2 miles, dz dt, which is what we want to solve for. So this will be 2 times 500 is 1,000, and I'm just going to leave that square root 3. And this will be miles squared per hour is equal to 4 miles dz dt. Divide both of these by 4 miles. And we're going to end up with 250 root 3 miles per hour is equal to dz dt. And that should be correct.
Yeah.
So, do you have any questions?
I'm pretty good. I'm pretty good on that one. I won't speak for Hayden. I will. I'm sure we'll get to it. But I must have missed the part about well, when we get to like cones and stuff like that. That part was a little troubling. But in terms of this,
Okay.
that's I'm good.
Okay. All right. So let's next do. Sorry, let me. Let's try number 19, maybe?
19. Oh, all right.
So here we have a man starts walking north at 4 feet per second from point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. At what rate are the people moving apart 15 minutes after the woman starts walking? All right. So, first things first, let's do some sketching.
Mm-hmm.
So we're gonna pick point P, which this is problem 19, by the way. Point P. And we have a man walking north. Right?
Yes.
We'll call him M. And walking north from point P. And we know that he is moving at a rate of 4 feet per second. Now we also have a woman who is walking south from a point 500 feet due east. So there's a distance between them, right?
Yes.
And this distance is 500. And that's not going to change. And then we have our woman walking south. That is, yeah, the correct directions. So what we're looking for is the distance between them, which we can connect via a line. This, oofta. But this is, yeah, this is right. Okay. So, let's start by, this looks like an okay diagram to you?
Yeah.
Okay.
To me, yeah.
Let's start by analyzing what we want and what we have. So what is it that we want? I'm gonna actually turn this into a solid line. And we can start labeling if you would like. Whatever you want to label, we'll label. I, for instance, would call this distance little m, and this distance little w. And I don't really care what this distance is. We can call it x, y, z. Doesn't really matter. Let's call it z. So, what are we given, and what do we want?
Oh boy, I'm given a lot.
Let's start with what we want then.
Oh no, I'm sorry.
No, that's good. We're given a lot. We have a lot of information to parse through.
Yeah.
What is it that we want from the end of this?
Well, so they want the rate that man and woman are moving apart after 15 minutes. So I guess that would be dz dt.
Mm-hmm. So the rate at which they're moving apart. Rate at which they move apart. All right, so that's a good start. Now let's take a look at what we actually have. And let's use the math, because we've labeled our figure, we can kind of start using that kind of lingo. So what do we have?
Okay, we have the rate of the man.
Mm-hmm. Which in Leibniz notation would be?
Sure, yeah. dm dt.
Mm-hmm.
For, yeah. We have dw dt.
Okay.
We have I don't know if I'm jumping ahead. I guess can calculate. We can calculate the value of m little w. I don't know if we're at that point yet.
Yeah, we could definitely
Right.
do that.
Okay.
So little w is going to be the easiest to calculate, or just w, you can call it. Right? So 15 minutes of walking. Actually, let's hang off until we know, do we need it? Yeah, we will need it. Okay, so 15 minutes of walking at 5 feet per second. What are we looking at?
If she starts 5 minutes later, would we do 10 minutes of walking?
It's 15 minutes after the woman starts walking.
Oh, after the woman. God, there are so many variables to this. So many things to this question.
There's a lot of information to parse through.
Okay, 5 minutes later, the woman starts walking. Okay, 15 minutes. Okay, got it. All right. So we have 5 feet a second times 15 minutes, but also times 60 seconds a minute.
Yep. So there's 900 seconds in 15 minutes. Times 5 feet per second. So we know that W is equal to 4,500 feet. Right. And then how many minutes has the man been walking?
So now this is flipped to what I thought it was.
Sorry.
No.
I went backwards.
No. That's fine, because I missed the part about it's 15 minutes after the woman started walking. So so is it still 15 minutes for the man as well?
Nope. He starts walking 5 minutes before she does.
And it's after 15 minutes of the woman walking. Okay, so it's 20 minutes of.
Yep.
All right, so then we have 4 feet times 20 times 60. 9,600, 4,800. Okay.
All right. So, at what rate are the people walking? Okay, so we're looking for dc dt. Okay. So, now we need to relate all of these variables together, related rates. What type of equation do you think that we're going to be using to do that?
I mean, are we going to be using the Pythagorean Theorem at some point?
Yes, definitely.
Yeah. Okay. I think maybe it's tripping me up because of
it looks
basically the triangles being inverted.
So let's draw a right triangle. Okay. We're gonna draw, like, are you okay with that?
Oh yeah, no, I'm sorry. Yeah.
Okay, so we're gonna draw ourselves a right triangle. We're going to extend this, right? So this is going to be the same distance W, right? The brown line is equal to the green line. And then across like this, which is going to be 500, because the blue is going to be equal to this. So now we've got this triangle.
Oh gosh. Right. Okay. All right. I see where we're going now.
Yep. Ooh, that's very strange. Okay. So now we have that brown triangle. And we have this distance, which is W plus M.
Oh, right.
We have this distance, which is 500. And we have this distance, busy.
Right.
Okay.
Makes sense.
So now we've got a triangle we can work with.
Yes. All right.
All right. So how am I going to relate these? Pythagorean theorem. We are going to end up with z squared is equal to 500 squared plus m plus w squared. Okay. So then we need to take this derivative, right? The first thing we're going to do, am I going to substitute this m and w in right here, or am I going to wait?
I mean, whether or not I know this to be right, for all certainty, I would have put that in to begin with. I mean, if we have 500, then
the question
we
is
also have.
Well, we have 500, and that's a constant. That's not going to change.
Oh, because m and w. Okay.
Is m of t. M in 2 seconds is going to be 8 feet taller. Right?
Sure. Okay.
So because these are functions,
Got it.
You're not going to sub them in. We could have called this like y or something and left it constant, but it is constant. Y is not a function of t. It's just a variable. Right?
Yes.
So the important thing to determine here is if we call something something, if we call it m, is it a variable or is it a function? And the way that you tell is if I alter the time, if I
right.
if I have like a YouTube video where I'm moving back to 5 minutes or forward 10 minutes or something, what changes? And if the answer is nothing, then you have a constant. And if the answer is everything, then you have a variable.
Got it.
Or rather a function. Excuse me. Okay. So because of that, we're going to leave those as they are when we're taking this derivative. So it'll be d dt. So d dt of z squared is equal to d dt of 500 squared is equal to, or plus, d dt of m plus w squared. Okay. So we got this pretty easy last time. What is this derivative? This first one here.
So this one's 2z.
2z.
dz dt.
Is equal to?
0.
Plus.
Plus.
This wonky thing.
Yeah.
So. I'm going to
square, that's right.
Spread it out a little bit. So this is going to be this is what rule are we going to use to find this?
Can we use the power rule?
Can we?
I'm obviously I'm drawing a blank, but I know there's a power rule. I can't quite remember how to distribute it.
Okay. Well, the thing with the power rule is that we use it on functions that are the form x squared or
that's just the power rule.
Yeah. So we're going to use the chain rule.
Right.
Because we have internal junk that's a function of t.
Yes. Yeah.
And then external junk.
I'm with it now.
So we're going to call m of t plus w of t something else, right? So m plus w is equal to f of it'll be f of t because both of these are functions of t or whatever. So it'll be f, we can call that f of t. And so if we were to take this derivative with respect to t, what would we end up with? F prime of t is equal to. Let me write this.
T plus.
Just think about it like this.
Oh,
So now we don't have that square.
oh, just dm dt plus dw dt.
Exactly.
Okay.
Precisely. Okay, so that's the internal stuff. Now what about our external stuff? Where I'll have this function I'll call g of f, which is equal to f squared. G prime of f is equal to 2f. So we're just using the chain rule. So to put it together, we'll end up with g prime of f, which is m plus w, right? Times f prime, which is dm dt plus dw dt. So, are you okay with all of that?
Think so.
Okay. Stop me if you're not.
Sure.
So we'll end up with something that looks like this. 2 times m plus w times dm dt plus dw dt. Okay. I'm going to clear some of this down here. And all right, so now we're sitting in a situation where we have got a lot of variables bouncing around. Most of them are on our have list. One of them is on our want list, and then one of them we haven't determined yet. I'm just going to rearrange this so that I'm explicitly saying dz dt is equal to 2 times m plus w times dm dt plus dw dt over 2z. So I'm going to have those 2's cancel because they can. So what am I missing? What is the one variable that we haven't figured out yet that's in this green equation that we don't have in the purple or the pink?
So, well, I mean, we want dz dt.
So that's in the purple.
Sure. We don't have z yet.
Nope, we don't have z yet.
All right,
okay. So there's our final hang up.
All right.
But now we know what w plus m is, and we know what 500 is, and we established that z squared is equal to w plus m squared plus 500 squared. So z is going to be equal to the square root of 500 squared plus, and then w plus m is just going to be w plus m, right? Because now we're living in the moment.
Sure.
Now we're saying z is equal to, like, if there's a set time t that this is happening at, which there is, the t is going to be equal to 15 minutes after the woman starts walking. So we're looking at a specific time. So at that specific time, m has a certain value, w has a certain value, and z has a certain value. So,
right.
Are you okay with using these to calculate what z is?
Right, because we're figuring out z at a point in time, so we can basically ignore the change factor of it, because they're those distances at that point in time. So we can just use those values. That's what you're saying, right?
Yep.
Okay, cool. I'm on board.
Awesome. Okay, so I'm plugging this into a calculator right now. It looks like it's going to be very large. I don't know why I'm surprised about that.
Yeah, right.
And it looks a lot less large now. So this is going to be 4,500 plus 4,800. So this is going to be approximately 9,313.43.
Cool.
And I'm pretty sure that's correct. So we can go ahead and plug stuff in. dz dt is equal to m plus w, which is 9,300. And what are my units for m plus w?
We're still working in feet. Well, that's not feet per second.
What are the units of w and m?
Feet?
Mm-hmm.
Okay, we're not per anything yet.
Nope.
Okay.
So 450 or 4,500 feet plus 4,800 feet. Yep.
Got it.
And then dm dt plus dw dt. It's going to be 9. And now what are my units?
Feet per second. Yeah.
All over z, which I said was 9,313.43. And then what are my units for this?
Well, that's just feet, right? Okay.
So I can go ahead and cross out these 2 feet. And so I know my final answer is going to be in feet per second.
Right.
And that makes sense, right? Because z is changing at a rate of, or z is changing how many feet per second.
Sure.
Are like differentiating them.
Like it's not feet squared per second. Like that wouldn't
there's no area
sense. Yeah.
The length of z and how the length of z is changing. So I'm gonna plug this into my calculator really quickly, and it's going to look like it's pretty close to 1. It looks like 3.43. So this is going to be equal to. Is that correct? 0.999. Seems too small. This is definitely too small.
I mean, the 9,300 over. Well, no, I'm sorry. Well, never mind.
Sorry, I did this in my last session today too. I just dropped something halfway through the problem. So give me a hot sec. Those 2's canceled, and that was legit.
Wouldn't it be closer to 9, roughly?
Did I just type it wrong?
Because if you say 9, if you just 9,300 times 9 divided by almost 9,300 would just be like 9.
Right. I'm sorry.
Oh no,
okay. Yeah, it's 8.987. So
okay, all right.
Liv can't use a calculator.
Listen, we got all the important stuff.
Important stuff is there. The final answer is wrong.
Well, it's multiple choice. I mean, I'll be able to make it the last bit of the way there.
Okay. So there's our answer. All right.
Cool.
All right. Do you guys want to start working through that practice, whatchamacallit, the self-assessment?
Is that like in this, like at the end of this, the end of the exercises here?
No, the actual self-assessment from Canvas.
Well, so like, you mean the actual quiz for the week? So here's the thing: the self-assessment is due Friday nights, and then your tutoring session is Sundays.
Yeah.
So I don't know if I can, like, I can't redo it. Like, I already did it.
Oh, yeah, no, Hayden just emailed me earlier
Am I
asking.
right?
Yeah, you can't redo it. Sorry.
No,
Um,
that's fine. And which is, I mean, just another reason why I'm continuing to come here, because I did the self-assessment and I'm like, what's going on? Because I must have missed a couple things.
yeah.
Um,
So, I think it would be like useful to walk through it. Just, like for the sake of like making sure like you're like up to par with exactly what the professors want from you for this course. But also, I mean, like it's something I can cover because you can't redo it. So
mhm.
it's like these questions are like totally cool for me to go all at.
Oh, I mean, I suppose
If you were
so.
to ask me to walk through the quiz and you still had like 4 hours left on the quiz, I couldn't do that. But
Sure.
I
Yeah,
can
right.
definitely do
Exactly.
the self-assessment right now.
I'm grateful that at least the quiz is available through Monday after your tutoring session, because that helps. I kind of can't do
Good.
anything about the self-assessment, so
Yeah. Um,
it's only 3 points, but yeah, it is what it is.
are you cool with making that switch then? Do you guys have access to the self-assessment after? Like, do you guys get to see the
I
problems?
I don't think mm, oh, let me see. I didn't think.
If you don't, I can like read and write them for you. But
Oh yeah, and so like what I said earlier, when you like for the last problem, when you said like, is everyone are we cool with this? And I said yes, but the issue that I ran into was like cylinder cone volume.
yep.
That was part of this. That was part of
Yeah.
the self assessment. That I'm like, I missed studying that. But I'm gonna see if you can open it. Yeah, I'm looking at them right now. So
All right.
if that's what you want,
Yeah. Let's do it.
um, you just me go like down the list.
Yeah.
Okay, all right.
Um,
Um,
so let's do this is the self assess. Is there one S or two S's? Oh, there's two. Uh man. Okay.
that's know what you mean.
I am not an English major. I'm not responsible for this.
Sure, yeah.
Um, okay, so question one. The radius of a circle is increasing at a rate of 5 centimeters per minute. How fast is the area of the circle increasing when the radius is equal to 2 centimeters? So, what equation am I going to be using? What do I want? What do I have?
Um, we have um, we have what the radius is at when we want to
Mm-hmm.
find out how fast the area is increasing, which the radius is 2 centimeters. Um, and we have the rate that the radius is increasing. So dr dt, 5 centimeters a minute. What we don't know is dA dt, or yeah.
Mm-hmm.
Sorry, I was trying to think of volume versus area, but it's just a circle,
Mm-hmm.
not like a balloon.
Exactly. So we have this area. We can sketch it out um, where we have a circle,
Mm-hmm.
and that's a little bit oblong, but that's fine.
That's not good.
Um, we have a radius. I think that's like fine too. Um, and so this is R, and R, I'm just gonna draw is, ooh, R is increasing. And so as R increases, then uh, the area increases.
Mm.
And so, like, as time goes on, it will get bigger and bigger. Okay, so we've established that. We know what we want, which is dA dt. How am I going to get it? What equation can I use?
Um, can I say how I set it up? And I don't know if I'm like jumping steps by doing this, or correct me if this is not the best way to go about. So um, I go like, what I've been doing is going straight to just saying dA dt equals the derivative of the equation for the area times dr dt. But I guess if we're just, okay.
What is the equation for the area? We'll call that A.
Sure. So it's what, pi r squared.
Yeah. Okay. So I would start with relating the area to the radius, right?
Okay.
And I would start here just so that I can say, I have an area that's changing. I have a radius that's changing.
Mm-hmm.
I have an equation that relates the area to the radius. So I can see if I look at this equation, if my radius goes up by 1, then my area will also increase. And that puts me at a position where I know that I'm like on the right path for figuring out what's happening.
So you're saying like,
yeah,
take a couple steps before, like a step before jumping into that. Okay.
Always write down the original equation, which might be one of the reasons that you were having trouble with the conical funnel.
Sure. Yeah.
So then I would take the derivative with respect to t, right?
Mm-hmm.
So you'll end up with dA dt is equal to, and then as we kind of wrote down earlier, dA dr times dr dt.
Mm-hmm.
And dA dr is equal to what?
So it's going to be 2 pi r.
Okay. Dr dt. Okie doke. So that is what I would do to figure out what my equation is going to be.
Mm-hmm.
And now I can go ahead and plug some stuff in because I know what I want and what I have.
Sure.
So this is going to be equal to 2 times 2 is 4 times 5 is 20 pi. And then what are my units?
So it looks like right now, just multiplying across, we have centimeters squared per minute.
Mm-hmm. And that should be our answer. And that makes sense because we have an area.
Sure, right, which is why it would be squared. Yep, and that looks to be it.
So yeah. All right, so there is question 1. Question 2. So we have a right triangle that is base B and height h. Suppose the base is decreasing at a rate of 0.5 meter per second, while the height is increasing at a rate of 2 meters per second. At what rate is the triangle area increasing when B is equal to 4 and h is equal to 5? Okay, so let's sketch this.
Sure.
And then I'm just gonna, one of the ways that I like to visualize this is like if it was, actually, no, we're just gonna leave it like this. Never mind, ignore me. That looks too equal. Let's do something like this. Okay. All right. So now we are going to go ahead and say we have the base, which is this a function? Is the base changing with respect to time, or is it going to stay constant?
Base is changing, so that'll be a function.
And then what about the height?
That as well, so h of t. And so I guess, I mean, consequently, that has to be...
Okay.
I mean, I don't know if we're establishing the hypotenuse yet, but...
Yeah. That is also something that I did, is I looked at this and I was just like, obviously we're going to use a Pythagorean theorem, but what we need to do is look at what we want. And what is it that we want from this problem?
We want the rate of the change of the area of the triangle, so dA dt.
Okay. And what do we have?
We have dH dt, which is 2 meters a second. And then we have dB dt, which is negative 1/2 meters per second, correct? Okay. And we have when the base is 4 and when the height is 5.
And I'm just like writing that like at time.
Oh, sure.
I don't know what time it is, but I know that it's like at a time, and that is the time that we care about. We could call it like T1 or something, but like that's the time that we care about.
Sure.
Okay. So, and I'm just doing that so I tell myself that B and T are functions and not constants.
Right.
So, what equation should I be using?
Well, I guess Pythagorean theorem.
How would the Pythagorean theorem help me?
Well, so hold on. We want dA dt. Are we going to try and find the area of the triangle?
Yeah.
Okay.
Do you remember the equation for area of the triangle?
1/2 base times height.
Awesome. So not only do we have the equation, we have it in terms of base and height, which are our variables. Next step.
We want to find we want the derivative of the area.
So let's implicitly differentiate.
Sure.
We can always implicitly differentiate. We can always pick a variable and say, this is how, like, and this is always time. In this section, it's always time that we're doing this with. So we'll end up with dA dt is equal to, and we can pull out that 1/2 for right now, right? Because it's just going to be a constant times the derivative.
Right.
And so this is going to be the function b of t times the function h of t. So how am I going to deal with this?
We use the product rule.
Yep. And so what is this equal to? What is the product rule?
So we have b times h prime plus h times b prime.
All right, so I'm going to rewrite this again in the blue. So I have dA dt is equal to 1/2 times b times h prime, which I'm going to put in Leibniz notation because that's kind of how we've been working with these related rates.
Sure.
Plus h times b prime. So it'll be 1/2 b dh dt plus 1/2 h dB dt. What do you think of this? We're not missing anything. We've got B, we've got H, we've got DH, we've got DB.
And then we can just plug in our rates of change of the height and base, right?
Yep. So this is 1/2, and then B is going to be 4. And
right.
What is the units for this?
Meters per second.
Is B in meters per second?
Wait, hold on. Oh, I'm sorry. It's just meters. Right. It's not changing. I mean, it's,
yep,
right.
You're good. And then dH dt is equal to what?
That is 2 meters per second.
And so this is a change in, changing a second increase. Okay. So, and then plus 1/2 times h, which is going to be 5 meters. And then dB dt is going to be negative 1/2 meters per second.
Got it.
So this will be 1/2 times 4 times 2, which will be 4 meters squared per second. Plus, or rather minus, 1/2 times 1/2 is 1/4 times 5 is 5/4 meters squared per second. And then 4 is going to be 16/4.
Sure.
So I can subtract those really easily, and I'll end up with 11/4 meters squared per second equal to dA dt.
And that's one that I got wrong, but I see the answer is there, so that's, there we go.
And the units make sense too.
Yep.
So
yes.
We know that we're on the right track at least. All of the units in the problem are the same, which is sometimes they do that where, you know, like they'll have one that's meters per second instead of meters squared per second, and then you'll know that you can cross that off.
Sure.
But in this case, that's not what they did.
Yeah.
Okay. So that was number 2. Number 3.
Here we go.
So we have a cylindrical tank. So this is not the like the funnel. This is just a cylinder.
Right. Okay. Yeah.
And it's got a radius of 5 meters, and it's being filled with water at a rate of 3 meters squared per minute. So I'm gonna sketch this out a little bit. Looks something like this. It's not precise, but what can you do? Right? And then I have this radius here. Okay. So here's my tank. I'm going to have a height, right? And so my height is going to be like this. And is my height going to be, or here, I'll just leave that as height, of the tank. And then I'm going to label my radius R. So what is the equation for the volume of a tank?
Isn't that one 4/3 pi r cubed?
That is going to be for a sphere.
That's for sphere. Okay. I'm sorry. No. I was just pulling that one out. Okay. This is pi r squared times h.
Yes.
That would make more sense.
We have a
Okay.
circle, and then it's moving up h.
Yes.
So this is h pi r squared. So this is for the volume of the tank. Okay. Now let's take a quick look. Let's write down really quick what we know about the tank. This is our halves list. So our tank radius, we know is going to be 5.
Yeah.
And we aren't given a height of the tank, which we'll get to later as to why that is the case, but we don't actually need the height of the tank. Oh man. All right, well, we're leaving the pink there. Because what we're actually concerned about is the height of the water that's in the tank. And there's more that's coming in from whatever source. So the volume of the water in the tank is going to also be represented by this equation. It's just that now height is a function of time. Does that make sense? Like if there's an extra cylinder in here, that is just the water. And it's got the same radius because the water's filling up to like all of the shape of the tank, but the height is varying depending on the time. Okay, so are you cool with how we're setting that up?
Yes.
Okay. We also have the rate at which it's being filled with water. So that is going to be equal to 3 meters squared per minute. What does that rate like mean in Leibniz notation? Like how would I write that down?
So wouldn't that be dv dt?
Yep.
Okay, good.
And one way that you could think about that is we have meters cubed per minute. And so that's a classic change in volume over time.
Sure. Like not a 2D surface, like a 3-dimensional, obviously.
Exactly.
Got it.
Okay. So what is it that we want from this problem?
So we want dh dt.
Mm-hmm.
Okay. So I think maybe this one tripped me up too, because like you're sort of splitting up. I mean, I don't know, you're kind of splitting up the equation for the volume. Like you're pulling the h out of, right?
Sort of, yeah.
In a way, okay.
Yeah.
Well, we can continue.
So we've got this equation, right? So I'm going to rewrite it down here. And we've got v, which is a function of h, which is a function of t, is equal to h pi. Is r changing with respect to time?
No.
So can I go ahead and put r in?
We wouldn't want. Well, because so we're not finding the derivative of the radius, right? So we're pulling that out. We're leaving that as 5 meters squared, right?
I mean, we could.
Okay.
Instead, I'm just going to go ahead and say this is equal to 25 h pi, or 25 pi h. Because the only reason this volume is changing is because the height is changing over time. The radius is not.
Okay, so I totally get this now, but this was tripping me up because you learn how to do something and then you try and apply that to every problem that you encounter. And so I was trying to take the derivative of h pi r squared. And then when I see
Leave
that
r as a
like
variable. Yeah.
you just compute r squared, you don't use the the power rule. That I was like, why is that a thing? And it's because the the radius is not expanding, it's only the height that's expanding.
Exactly. So
Got it. Okay.
because the radius is not a function of time, if I were to take right, if I were to take dt of the radius, it would be 0, right? Because
Right.
the rate of change of the radius with respect to time is 0.
Right, just like when in the Pythagorean theorem with those problems where one of the variables is unchanging.
Yeah.
It's just
exactly.
a constant, it's 0. Got it. Okay.
The rate of
I'm
change
with
of
you.
that one is 0. So
Got it.
all right. So now I have an equation that is easier to work with. And I am going to implicitly differentiate with respect to time, because that's what we do in this section. And I'm going to end up with dv dt is equal to what? What is this going to be equal to?
So we'll leave the 25 alone. Well, actually, I think we'll leave the 25 pi alone. And we'll just have that times dh dt.
Exactly.
Okay.
Awesome. So this is probably a lot easier to work with than what you were trying to work with when you left the r there.
Even getting to this point makes it so much. Okay. Makes more sense. I didn't even get to this point before. So that's good.
So what we can do is we can just rearrange a little bit. And so we'll end up with dh dt is equal to dv dt over 25 pi. And dv dt, we said, is equal to 3. So this will be equal to 3 over 25 pi meters cubed per minute.
Oh, that makes so much sense. Now.
Yeah, unfortunately, hindsight is.
Yes, yeah, it very much is. Okay, cool. I'm totally on board with that.
Awesome. Okay. So clear. Now, number 4. I went ahead and did these problems like on my own, and then like it lets me like pop in and like check my answers. And this is the one that really screwed me up because I can't do anything with angles.
Oh,
gives me an angle, I resent everything.
Obviously you know more than we do. So, but like the fact that like that was tripping you up, I can't figure out. Like, I remember dealing with radians and converting from degrees to radians in trigonometry, and like I kind of get that. But when we're talking about the rate of change of an angle, I like everything stops working in my head.
Yeah.
Yes, I'm glad that we're going to do this one, because this was like one of the biggest issues.
Yeah, so this is the bane of my existence.
Cool. So we're
in the same boat.
Let's figure it out.
Me a lot of time, honestly. Like, it took me a hot second to figure out what was going on here. And that's just because I hate angles. So we're gonna build this, and we're gonna do it right.
Cool. Cool.
So what we have a kite that is 100 feet above the ground.
Okay.
Right?
Yep.
And so we're going to call that, I'm actually going to color code this, I think. I think that might be what I need to do. I'm going to call this, I'm going to pick a color that I'm not going to actually use. And that is going to be what this, I'm going to call this, like the height above the ground is going to be y.
Sure.
And that's going to be 100 feet. And And then I'm going to call this x distance x, and then this z distance, well, this will be our z distance this long way. So we have moving horizontally at a speed of 8 feet per second. So if that is x, then what is this 8 feet per second going to represent?
dx dt.
Yep. Okay. And we are given, we've got, I don't like that. Pick something that pops. So that's our z. We're given z is equal to 200 at the time. So z is changing as the kite moves. So z is a function of t. I also believe that y is constant and x is a function of t.
Mm-hmm.
So we have it moving horizontally, kind of like our airplane did. It was moving horizontally, so the distance is making that change, but the total like altitude is unchanging.
Yep.
Okay. So finally, we have our angle that we need, which I'm going to call theta. And theta is the angle between the string and the horizontal, right? So horizontal and then the string.
Got it. Yep.
So that's how I labeled my theta.
Yeah, with the yeah, and like so, I'm with you. Like so far, with you 100% on the setup of it.
Yeah, it's later on that gets really messed up,
Yeah.
So, what do we want?
So what we want would be d theta dt.
So the steps to getting where we want to go include finding an equation that yields d theta dt. What do I mean by that, yields? What I mean is if I have a function, for instance, sine of theta, if I were to take the derivative with, this is theta of t, right? So theta changes with respect to time. If I were to take the derivative of this with respect to time, then I would end up with the chain rule, right? So I'd end up with an end result of cos theta of t d theta dt, because this would be d. So we could call this like, I don't know, we could call it a. This would be dA d theta times d theta dt. So that's what I'm going to use to get d theta dt.
Okay.
That's where my brain is going right now. Which is not the most straightforward place to go.
Sure.
But that's kind of thinking very meta about this whole situation. Another way to think about it is that I just want to introduce theta into my life, right?
Yeah, sure.
I want to be able to relate theta to something.
Sure.
Something that would be really nice to relate it to is y, because y is being held constant, right? So that's where I'm thinking.
Well, I mean, because so this kind of seems like, I mean, there's probably an easier versus a harder way to go about finding this out, but since you could, there's different ways of determining theta because you could use sine, cosine,
Mm-hmm. Oh yeah.
tangent. So so essentially, like in your mind, easiest way would be whatever trigonometric function of theta that includes the constant. 100 is probably going to be the easier way
Yes.
to get it. Okay.
My gut reaction is if I used cosine, I would be using x of t over z of t, and that would make my life hell.
Yeah, sure. Sure. Yeah.
I am always looking for the easiest way.
Well, listen,
So,
like if it gets you the same answer, why?
so the equation I'm going to use sine, right? And so sine is opposite over hypotenuse.
Mm-hmm.
So the sine of theta is equal to the opposite, which is going to be 100, over the hypotenuse, which is going to be z. Noting that both z and theta are functions of time.
Mm-hmm. Okay.
So I'm actually going to rewrite this a little bit because that's how I go. C to the negative 1. And then I'm going to differentiate with respect to time. So I have ddt of sine theta of t is equal to dt of 100 z to the negative 1, or z of t to the negative 1. So what are these sides going to equal?
Wait, did we lose cosine somewhere?
Nope, there was no cosine.
No, I meant, so we have ddt of sine. Sorry, I'm just missing the part on the right side of the equal sign.
So this is 100 z to the negative 1.
Okay.
And the reason I did that was because sine is equal to opposite over hypotenuse. So it'll be 100 over z is equal to sine theta, right?
Yeah. No, I got that. I think maybe, so the sign that's in the oh, never mind, I'm sorry. Right, because sine is just saying what is the 100 over the, okay, I'm sorry. Yep. Continue.
Nope, you're good.
Okay.
Stop me if something becomes unclear.
No, you substituted sine for 100 100 over z.
Yeah.
Right. Okay.
So,
Yeah. Got it.
I made a statement that was true.
Got it. Okay. Yeah. Right.
Yes. I'm not looking to do like inverse sine or anything like that. This is a true statement, so I'm going to differentiate it.
Got it.
Okay. So, all right. So what is the derivative of the sine of theta of t?
Cosine theta t.
Okay.
Times what was that? D theta dt?
Bingo.
Okay.
And the reason that we did that was, if you remember, if we had A is equal to sine theta of t, right? Then dA dt would be equal to cos theta, or dA dt would be equal to dA d theta dt, where dA d theta would be equal to cosine theta.
Okay. So that really does help, because I remember in like a week or two ago, like this was a couple weeks ago, that breaking out like the theta from the trigonometric function, and taking the derivative of that was like tripping me out as
Yeah,
well.
no, like
It's
if you have something that's in a trig function and we're working with derivatives, then you're not going to use like anything to get it out. The way that we got it out here was because we implicitly differentiated,
okay.
not because it's like the chain rule, and we can use implicit differentiation.
Got it. Got it. Okay. All right. I'm still with you.
Okay. What about the second one? 100 times d or 100 times z to the negative 1.
Oh, negative 100 z to the negative second.
Times, because we're differentiating with respect to t.
dz. Wait, dz dt.
Basically, if you remember from implicit differentiation last week, if we had like y and then we wanted to take the derivative with respect to x, we would just call it dy dx. If we had y squared, it would end up being 2y times dy dx. So regardless of like what we're doing with like this, like it's basically like we're doing like the chain rule. So if a is equal to y squared, then dA dt is equal to dA dx dx dt.
Okay.
Or I swapped my variables. I'm sorry. That probably did not clarify anything. Bad lift. So this is y as a function of x. So dA dx would be equal to dy dA dy dx.
Okay.
And so a is equal to y squared, dA dy is equal to 2y, dy dx is equal to dy dx.
Right.
So
when you do that, I think that's one fault of like the text is that
they assume you know everything.
Yeah, it does. Yeah, it doesn't like it.
Everything.
Yeah, like it just says this equals this, and it doesn't say like if you do this and you break it down in like just like you did like dA over dx equals d over dy dx like, and that's how you get to the next step. Like it's like it skips middle steps where it explains what it did. That's I think a shortcoming of that.
That's a mood. Yeah, that's common for a lot of math textbooks, though.
Yeah, it's
okay.
Okay.
So hey, look, we have an equation that has d theta dt in it, and that's what we need.
Yeah.
Dang. Let's use this.
It's awesome.
So we've got what we need. Well, we've got something of what we need, right? And so I'm going to rewrite this. I think I'm missing something. I'm definitely missing something. I'm going to check and see what it is I'm missing in a sec. I'm going to rewrite this as d theta dt is equal to negative 100 z to the negative 2 dz dt over cos theta. Okay. That's where I'm at right now. I'm missing a lot of things. I know z. I got that. But I am missing dz dt. Right? I don't have that. And I don't have cos theta. Right. So how am I going to go about finding that? I'm going to erase this stuff about finding this implicit. Okay. So. first things first. Let's go back to our list. What do we have? What do we have that we haven't used?
Okay. So we don't have dz/dt. I'm sorry. Wait. Yeah. I'm sorry. You did just say that just there. We don't have cos theta. I mean, like, cos theta would just be x of t over z of t.
That's true, but the thing is,
we don't want to.
Yeah,
do that, right?
I'm trying to get this down to a number.
Sure.
And so introducing more variables into this mix right now,
Yeah,
is not something I want to do, because I don't know yet what x of t and z of t are. And really, all I know, I know how x of t is changing. That's something I haven't used yet. But I don't want to get into x of t over z of t is equal to cosine theta right now. That is a good gut instinct, though, is look at what we have.
yeah, and I saw that, but I agree also with what you're saying. Is it almost seems like it would move the problem backwards in terms of being able to figure it out.
Okay, so what is the shape of our problem right now?
Sorry. You mean like the thing in the bottom left that you have written down?
No, I mean, like, the answer I was going for was a triangle. And what do we like to do with triangles in this section?
Oh, you use the Pythagorean theorem.
So,
okay.
I can use that to find...
Oh, to get us our value so that if we take the cosine, we're not just substituting it for variables. Okay.
Exactly.
So, we know, oh dear. Sorry, it told me my internet connection. Okay. So we know what we want, like z at the time of what we're trying to figure out is. So we could take 100 squared plus x squared equals 200 squared.
Okay. So that would be x squared is equal to 200 squared minus 100 squared. So x is equal to
square root of 30,000.
Something like that. 200 squared. Oh, sorry, I'm putting it in calculator right now.
That's all good.
Plus. Oh shoot! Is this? Hang on. I gotta put. I'm using my phone as a calculator, which is admittedly one of the worst calculators on the planet.
Oh, like the iPhone can do everything except for like squares and square roots and trigonometric functions. It can, but not.
Okay.
Well.
Wait. This is simple. So this is simpler than I think it is. This is
yeah, I think it's 30. 30. Yeah.
So that is equal to 10,000 times 3, right? And the square root of 10,000.
100 square root 3.
Yeah.
Yeah.
Okay. Just gonna write that down. Okay. That keeps decimals out of the mix. Okay, so now we have x. And we have z. So we should be able to put this in and say, sorry, this is my notes right here. I did these problems beforehand and my notes are a wreck. So I believe we can say that this is equal to
Um,
100 root 3 over 200, which would be root 3 over 2. So now we have that.
um, I will say, I don't know if you saw, Hayden was asking the cos on the bottom, does the cos on the bottom of the fraction equal 1?
No.
I don't
Oh,
know
I'm
if
sorry. I
the,
totally didn't see that.
yeah, literally just,
Um,
oh, L, oh, is that
first of
like,
all, when were you working with L'Hôpital's? And
uh,
second of all, not
I'm not going to be able to help on that.
practice midterm?
Oh,
Were
dear.
you taking the practice midterm for Calc 1 or Calc 2? That should not be until Calc 2. L'Hôpital's is 141 stuff.
Oh, boy.
Okay. Maybe they screwed up. Oh my god, that's so funny. Okay,
It's
I'm so sorry.
so, I,
I will look at
uh,
that and check to make sure that that's what it needs to be. Like
I,
L'Hôpital's finding like limits of like you use it to find limits of stuff. And in this case, we're not finding a limit. So we're not really thinking about L'Hôpital's rule because we're not finding a limit. What we kind of want to do is like pick and choose, like not pick and choose, but like figure out what everything is equal to. For instance, we need z, we need dz dt, and we need cosine of theta in order to figure this out. And so the way that we went about that was by just solving for all of this stuff. So I will take a look at the practice midterm and
yeah, I guess I should too.
um, okay. I'm fairly confused by the fact that that's on there, but you guys didn't cover that, right?
I, I'm, well, okay, I was going to defer to Hayden on this one because like I've lived, like I've said to you in the past couple weeks, I have to be completely honest, have not used the textbook that much because it's because you know which one compares to which in the two
Yeah.
different books. I don't think that is
Well,
stated on
oh,
Canvas which one
yeah.
converts to which. So I've just been going by the instructions,
Yeah.
the videos and stuff. So I'm not sure. I'm not sure about.
Hayden, this on the bottom here. This isn't a 0. This is a theta. So the cosine of 0 is equal to 1,
Uh,
but this is a theta. Is that
okay? That makes more sense
okay?
to me now.
When taking a limit, taking a limit of cosine of theta? Okay. I'm not sure what's happening. And I'm pretty sure that that's not on your exam. I hope that it's not on your exam.
Ditto.
So, all right.
Okay.
Let's just go with, we've calculated the cosine of theta by saying that it is adjacent over hypotenuse. And our adjacent is
Mm-hmm.
going to be our x, which is 100 root 3, and our hypotenuse is going to be our z, which is 200 at this time. And the only reason that we have an x value here is because we are saying this is x at this certain time that we're calculating this, right?
Mm-hmm.
So now we're in the, like, we've narrowed it down from a general, like something that is generally happening to something that is happening at a specific point in time.
Mm-hmm.
Okay, so we've got a cosine of theta. We are still missing dz dt. We are on our way. How do you think we are going to be able to find dz dt?
Um, that
I'm going to,
shoot. Um,
what we do with a right triangle is we take the Pythagorean theorem. So,
right. I'm looking back at my notes from when I took this quiz, and I actually got like real scary close to where we're at right now, but I think I couldn't stick the landing.
Yeah, it's like it's not. It's this problem
It's
really.
it's not intuitive.
Yeah. So we're going to take the derivative with respect to time of this equation, right? Because this is how
Hmm.
the triangle is changing. And that will allow us to learn how z is changing as the triangle is changing.
Sure.
So it's going to be 0 plus 2x dx dt is equal to 2z dz dt. Are you okay with going straight from here to here?
Oh yeah, right. Yeah, I'm with you. Yeah.
Okay. And now we can do some subbing in because we know what x is and we know what dx dt is. So we have 2 times x, which is 100 root 3. And this is in feet.
Hmm.
And I'm switching back into units here so I make sure that everything's on the up and up.
Hmm.
And this is 8 feet per second. And then I'm going to say that this is divided by 2 times z, which at this time is going to be 200 feet,
Right.
is equal to dz dt. Oh, not dzt. So these 2's are going to cancel, these feet are going to cancel, and I'm going to end up with 800 root 3 over 200, or 4 root 3 dz dt.
Okay.
So I have dz dt, I have
Yes.
cos theta, and I have z. So I can put stuff into this dark green equation here now.
Okay. Got it. Okay. So we established what the equation should look like way back there, and then we just had to figure out all the things that were missing.
Mm-hmm.
Okay.
And another, I can just go ahead and instead of putting z up top, I'll say that this is divided by z squared, which in this case is 200 feet. Then cos theta is going to be root 3 over 2. And then, oh, and I'm still missing dz dt is, sorry, I did this in a very roundabout manner because I wanted to get the z down there, which
That's
was
all right.
useless, objectively speaking. So those are my pieces, dz dt, z,
Mm-hmm.
and cos theta. And this is going to turn out to be negative 400 root 3 over, this is 200 divided by 2, so 100 root 3. Am I right? I don't think this is, I'm missing something.
200 feet squared.
It's squared. Aha. Okay. So this is
40,000?
yeah, this is 40,000, I believe. Yeah, root 3 over 2. So negative 400 root 3 over 20,000.
Oh, can we cancel out roots?
Yeah, I mean, they're just
Okay.
numbers.
Yeah.
So if these were both times root 3, and then 400 divided, or here, 20,000 divided by 400 is 50. So this will simplify to d theta dt is equal to negative 1 over 50.
Yep. That's one of the answers. That's not the one I got, but that is there. Okay. So I'll tell you what, like, there's not like an easy, like, there's not an easy path to get to that answer.
No.
That's insane.
Yeah.
Oh man. Okay. Yeah, I think the other thing that threw me off from this too was like, so the WebAssign, we can go on and do the homework questions. It was recommended just like do practice examples of all those questions. So just like keep resetting the values and just do them again. These didn't show up on this week's this didn't show up on this week's homework. So I think that was another reason too, that maybe this didn't come on my radar, so to speak. So
and this brings in like trig. This brings in a lot of stuff. So
yeah,
this was a hard problem to tackle.
sure.
I
Keep doing it, I guess.
tackling this problem.
Yeah.
So let's move on to question 5 and rid ourselves of this evil.
Yes, yeah. I know this one's going to be
done with it. This is, I mean, this stuff, like, you just the same systematic approach, and it's good. Okay, so number 5, water is flowing at a rate of 5 meters cubed per minute into a tank. The tank is a cone with an altitude of 20 meters, a base radius of 10 meters, and the vertex is pointed down. How fast is the water rising at the time that it is 8 meters deep?
A lot of stuff.
Yep.
Yeah.
So, there's a cone, and we are going to say that it is h tall, or rather, it is 20 meters tall, and its base radius is this, and that is 10 meters. So do you remember the formula for the volume of a cylinder? Or not a cylinder, sorry, a cone.
A cone. I don't. I know it's there's a pi and there's an H. That's I can look it up, but
yeah. So this is just something that you'll want to be a little bit familiar with. There are some standard ones that'll show up on exams, and that is sphere, cone, and cylinder, in addition to your like circle and square and or rectangle and triangle sort of things.
Yeah.
So
those I got. Yeah, I think it's because I've never dealt, like, I think until now I've never had to deal with a cone, which is why like the other ones I kind of got. Yeah.
Yeah.
Just remembering it's not too hard.
Okay, so we don't want to deal with this in terms of 2 variables. If you remember the cylinder problem where we had the tank that was filling with water, you remember how hard it was to deal with having both a height and a radius, and thinking that they both were changing. In this case, the radius is changing as time changes.
Oh, yeah.
Which is
right.
awful. But we can relate the radius over height is going to be the same ratio throughout this the cylinder. So we can just use a ratio equivalency to say that the radius over height is always going to be equal to the ratio of 10 to 20.
Okay.
So the radius is always going to be equal to 10h over 20. I just multiplied by h, which is h over 2, if I divide both by 10, right? So I can say that the radius is going to be equal to h over 2.
Oh, all right.
So then I can go back to my original equation. I can say this is v is equal to 1/3 pi, and then h over 2 squared times h,
All
Yeah,
right.
this is h squared over 4 times h. So our final equation that we're going to get for the volume of the cylinder is going to be V is equal to 1 over 12 pi h cubed. Are you good with that?
Oh, I'm sorry. Oh, I'm sorry. Because you're right. Because you're just multiplying the 1/3 through
Yep.
to the h squared over 4, and then you just multiply the h. Okay, yeah, got it. Right. Got. We just combined like terms. Got
Yep.
it.
So now I can scrap that because I don't give I don't care about that anymore.
Sure.
I can just scrap it. This equation gone. Now I can like look at what I really care about, and that is relating the height of the water to the volume of the water. So let's make a list of what I have and what I want. What do I have and what do I want?
Okay. All right. So I guess we're going back to the beginning.
Mm-hmm.
All right. So we have the I guess dv of dt is 5 meters cubed per minute.
Mm-hmm.
Okay.
That's the rate of change of the volume.
Okay. I always just, it just takes me a second to think, like, I know that it's telling me something is changing. I'm just having to okay, water flowing in means it's the volume. Like, I just have to give myself that reminder. Okay. And I guess we established, well, yeah, we already established all the other things. Or, I mean, do you want us to state that we can put radius?
Well,
Or 8 meters deep.
yep.
That's, yeah.
So we're going to rewrite this. So now the height is going to be the height of the water, right? Because just like the cylinder, I don't care about any part of this cone that is not filled with water.
Sure.
And I know that I can relate the height of the water to the radius of the cone. So I did that. So I should just be able to use h is the height of the water instead of the height of the cylinder, right?
Got it. Like a cone within a cone.
Mm-hmm. Okay. So then what do I want? What is my goal out of this?
So they want us to find okay, so what rate? So I guess they want us to find dH/dt?
Mm-hmm.
Okay.
They want to know how fast the water is rising. And
Right.
that means that we're looking at the change in the height
Got it.
of the water. So we have an equation. We have what we have. We have what we want. We've got a nice little diagram. And we've established what's happening here. So let's just do it. What's my next step?
So we know what height we want it to be at when we're determining the rate. So, well, actually, I'm sorry, before we get there, should we take ddt of this?
Yep. Implicitly differentiate with respect to time.
Yes.
And we end up with dv dt is equal to what?
We can take out the coefficient, so it's going to be 1/12. Okay, right, got it. And now I don't want to height So are we going to do just h cubed? No, I'm sorry. The height is changing. 3h squared.
Exactly.
Okay. I was getting confused again with the previous one where the radius wasn't changing, but this is actually changing. Okay. Got it.
And then what are we missing?
dh dt.
Yes.
Okay.
And we're doing that again because we have dv dh times dh dt, because we're using it as a chain rule, and also because we want dh dt. We can't forget it.
Yeah.
Because this is like what we're going for here. So I'm going to simplify this a little bit. This is going to be dv dt is equal to 3 divided by 12. So this is going to be pi h squared over 4, right? So the 3 is going to be divided by 12, dh dt. So what we can do is we can say that this is dv dt divided by pi h squared times 4 is equal to dh dt. And now we can put everything in.
Right. So we have, brought the 4 up, okay. So we have 5 meters cubed per minute. Times 4. And I guess now we can sub in 8 for 8. Okay, you subbed in 8 for, so that's squared. And so now it's just arithmetic, right? So 20.
Oh, it's 20, not 9.
Oh,
I just added
like,
it.
what's happening? 8 squared. So we can cancel the yeah, and so we'll be left with what? 5 over why can I?
Yeah,
I
always,
5
The
5
way I do it is I
over,
would say this is 10 over 32
and
pi,
then yeah,
5 over 8 pi. No,
yeah.
5 over 16 pi.
I was trying to do too many divisions in my head. Okay,
Yeah.
but yes, so we canceled out the meters, and so just left with meters per minute. That's awesome, and like such a nice palate cleanser to the previous problem.
Yes, very much so.
Tell you what.
That one didn't, yeah.
But okay, no, I follow that, so that's good. Got it. And I'll tell you what, I know we talked about this last week, but the putting your halves and your ones, like it helps.
Yeah.
I mean, you really need to.
This is a lot of material to digest. So I mean, there's a reason we're only doing one section this week, and this is the reason. So yeah.
Makes sense.
Yeah. Yeah, that is definitely not unusual. So like this class is, it's very difficult in that you think that you understand, like you think you know how to do the problems, and then you get thrown a problem, like maybe problem number 4, where you know how to approach the problem and you can get partway through it, but you just can't seem to like hit it home.
Yeah.
Make it happen at the very end. And so that's not abnormal at all, that despite the fact you're feeling confident, you still are getting 80s. The thing that I would suggest to combat that is just practice, practice, practice. One thing that helped me was to kind of like make like a list of like all of the different types of like problems, maybe. Like you would get stuff like water flowing into a tank, like problems, and then I'd make like a sub list that would say the tank could be a rectangle, the tank, or like a cube, but the tank could be a cylinder, the tank could be a cone, and just kind of like work through like, am I aware of what all these equations are? Am I aware of like how I would approach this? This is not an easy class. This is not an easy class. So my biggest suggestion is always just to practice.
Sure.
And to write everything down. Don't ever assume that you like can just like think your way through a chain rule real quick. Because if you differentiate wrong, then everything down the line will be wrong too. So that is what I suggest. Yeah, that is also very frustrating. I would agree. Only having, like, you can't miss anything, and it's very frustrating. So I'm with you. I get it.
Yeah.
I do.
I'll tell you what, like to that point too, that he's saying, like when I've done online, even with my trig, I took it hack, but you do online math homework assignments, and they're like out of like 10, 15, 20 points, but like these are like their fractions of points on the web assignment. So you do like 15 problems and you have like 4 points. So I think it makes it harder to like overcome getting 1 or 2 wrong.
It feels, yeah. It's a rough class. This class is notoriously rough.
Not for the faint of heart.
Yeah. Yeah. Are you guys going to be using this stuff just out of curiosity? Like, what are your majors?
Oh, sure. For me, mine will be hopefully I get through to the end. Software engineering.
Okay, industrial engineering, software engineering. This stuff you are going to be using, especially you probably, Hayden.
Well, I'm taking this congruent with C++ programming right now, and like even in that, like you're putting in equations, and like if one step is wrong, it throws everything off. So this helps, you know.
Yeah, and Hayden, for you in particular, I'm not like a huge expert on like the engineering like process at like Penn State, or generally speaking, because I'm a STEM major, like a science major, no, not STEM, but like a science major, science, and engineering people tend to use a lot of this related rates type stuff in relating, like if you're like making something. Or I know somebody who's taking like a flow class right now. It's just like fluid mechanics basically, and it's a lot of this type of stuff.
It's insane. Like it sounds like a whole class with just these problems.
Yeah, the professor is really, really funny too, in that he's really cruel in that he schedules 2 exams a year, which is always the Monday after Super Bowl Sunday and the Monday after spring break.
I'll tell you what, you know, like
his exams run from 8 p.m. to midnight every time. Oh my goodness, yes. How did you know? Yeah, it is him, as we can see in the chat. But yes, he is infamous. That is true.
That's funny.
That's a mood. But yeah. Yeah. I would just say practice. Also, if you're in University Park, the people who hire me is Penn State Learning. And they have live tutors at 2 locations. Like, you can just walk in with your homework and say, can you help me? And they will help you. And that's in the Buki building and the Sparks building. Yeah, they do. They do cut you off.
Wow, like 30 minutes. I mean, like I feel like problem 4 was 30 minutes. Yeah, right.
Yeah.
Yeah, right. Oh, geez. That's rough.
But I don't know how many times you can go because I don't do the live tutoring, but I know that if it's like not busy, sometimes they'll just let you stay, or they should at least. That's what
I
they told me when I was taking my tutoring class, is that they could just let people hang out there for however long.
so obviously Hayden, I'm obviously learning this just like you are. Not an expert in any of this, but like, so when I was hitting a real roadblock at the beginning with like, I couldn't even like get down like the chain rule and stuff like that, and more comfortable with that now. But I literally went online and I found places that had like, give me a list of examples using this and the answers. And so then I would just like I would just do them. I just print it off and just do problems that provided the answers and then just compare it to just do that. Just practice that way. And that helped. So that's what I'm going to try and do with these too, I guess.
Yeah.
Just find a bunch of rate of change, rate of angle change, problems and do those.
Yeah, that's the most annoying thing. The way that I would suggest fixing that is just writing everything down. Yeah. And always relate back to the front of the problem. Like, when you end up with an answer, like here we ended up with 5/16 pi meters per minute. And we know that makes sense as an answer because the units work. We know that our height is changing at a rate of some meters per minute, and it makes sense that it's positive because our height is increasing as water is entering the tank. So it's
Like
always
you're saying,
great.
like use like common sense to like, if
Yeah,
you said like 5,000 meters a minute, like something went wrong.
yeah, especially if your tank is 20 meters tall.
Yeah.
So it's just like, just go back and check at the beginning of the problem to see if your answers seem like they're the right sign, and if yeah, I would do all of the practice exams. I will be hosting a midterm review next week. I believe we don't have any content next week, and it's just like midterm practice stuff.
Oh, that's great.
If we do have content, then I will hold like an extra session probably for the midterm review. But I'll have to go back and check the course. But yeah, practice. Just like I said, I always like make a list of like, this is what's going to be on the midterm, like starting at like limits, like how do I find a limit, and ending at like, this is how I've been applying the stuff that I've learned. And I love related rates problems because it is applying the stuff that you've learned. Like, this type of stuff includes implicit differentiation, for instance, which is a way that they can test you on that without explicitly saying implicitly differentiate this.
Right. They just give you a problem to use it in.
Yeah. Related rates and optimization are key points where that happens. So yeah, that is what I would suggest.
Cool.
Okay. So trig stuff. My big suggestion for trig stuff is getting familiar with the unit circle. And like, where'd my pen go? Like, if you have like the unit circle, like being able to like, I don't know why I just drew a circle and then I like was gonna fill it in, but yeah, the unit circle is confusing, but it is like a really good way of being able to like figure out what exactly is going on. It's been a while since I've used it, but I'm pretty like I would definitely just say that like unit circle stuff is your friend. And that's what I would recommend for dealing with the trig. This is the wrong angle. So, yeah.
When I first looked at the graph of all the values of the unit circle, my head exploded.
Yeah, the unit circle can be confusing. There's probably a good Khan Academy video about it. And I think there are some resources at the beginning of the module section on working with like trig. Otherwise, it's just, I mean, the way that I get away with not memorizing what cosine pi over 2 is by using the unit circle. Another way that you could think about trig, besides the units, well, I mean, it is the unit circle in essence, but is to think about like the graphs. If you have the cosine of pi over 2, right? So this is pi, and this is 2 pi, and then pi over 2 is going to be here at 0. And then this is like a cosine graph, and then the cosine at 0 is going to, like, this is only works for like some of the key points along this curve, but that's another way you could maybe think about that. That's easier than thinking about the unit circle. But unfortunately, unit circle is your best option.
So, like on that note, I don't recall. I think I only recall like one problem over the last couple of weeks that required like converting from like cosine pi over 2 is the same as the degree angle. Like we haven't used that
you
much.
don't use it a lot in this class, but issue
I suppose when it pops up,
they reserve the right to do so. So
sure.
When they do, it's shocking.
Okay, that's kind of evil.
Yeah.
But requires that you, I guess, understand.
So
okay,
I would not make the unit circle a priority of your studying, but if you have some spare time, then committing that to heart would probably be good just for
got it.
Figuring out what's going on.
Cool.
Okie doke. Do you guys have any extra questions?
No, I think 2.5 hours of practicing. This is probably like all that the brain can take.
Yeah, I'm like getting a little hoarse. Just like chokes. Okay.
Yeah.
In that case, let me know if you have any extra questions. Like I said, if we actually are covering like content next week, then I'll add an extra session for a midterm review. If you have any questions or types of questions you want to cover in the midterm review, feel free to email me, and I'll make that happen. But otherwise, let's just plan on next Sunday at 5.
We don't think because I didn't look ahead yet, which is do we think that there's not like, is next week supposed to be just
some
review?
classes
Does it depend?
My other class that I GSG for is 110, and they usually like have like a whole space for the midterm.
That's, I mean, I feel that's, I mean, listen, this stuff is tough enough to like, to get like a week to study and understand it. I feel is warranted.
6, yeah, it says week 6 is midterm exam 1. Your practice midterms are available until the 18th of February, which is a week and a day from tomorrow. And then week 7, interpreting derivatives, which is section 2.9, which is the next section in the book.
Okay, so we skip over it, or this week is between 2.8 and 2.9.
What it looks like. So the weekly quiz for quiz 7 does not have a due date.
I did see that the next homework on WebAssign was 2 weeks apart, so that would make sense.
Yeah. Then
cool.
Next Sunday at 5 will be the midterm review session.
Awesome.
And yeah, there are there are 4 practice midterms available.
Wow. Okay. Well,
And there are definitely more on the math department website.
Okay. Are they just different iterations? I mean,
Yeah.
I won't. I mean, I won't keep you. I can find it. I'll find this stuff out, but I
They
want to
should
keep.
just
Yeah.
be, yeah, different iterations. I don't know if Hayden's still here. Is he?
No, I don't believe so. No. Okay. Yeah, I'll take up. I
So I,
appreciate.
I I have no idea which one is the one that uses L'Hopital's rule, but I think it's safe to say that since the last time I dealt with teaching that, I was in a class that was Calc 2. That
Yeah.
you don't have to worry about that in.
Yeah, I sure hope not. I mean, there have been a couple. I think I mentioned last week. I actually, I don't know if it would have been changed had I not mentioned something, but there were homework problems on the WebAssign that were part of the following week's instruction. And so I'm like, I don't understand any of this stuff. And I said something, and she went back and she changed the WebAssign problems to only include this week. So I'm hoping that that thing is not is not on the midterm.
Yeah.
I'll just
That
go off of the practice midterms and
that shouldn't be.
practice
The
problems.
practice midterm should be a fairly good representation.
Good.
I never had a problem with them before.
Like they were good. Like they were adequate
Yeah.
prep thing.
That's basically how I prepped. I actually, yeah, I found a lot of my old, like when I was originally taking Calc 1, like
Mhm.
material the other day, and it was just like booklets of practice. So,
Right. Yeah. I guess that's the best way. Yeah.
so yeah, um,
All it's
that's what I have for you tonight.
that's no, that's great. Thank you so much. You dedicate so much time
Of course.
to it on Sundays, and
That's what I'm
I
here for.
appreciate it.
Um, I will see you next Sunday, probably. If something comes
You,
up, don't feel bad about it, but
yeah, no, you will see me next Sunday.
um, I hope you have a great week in the time being.
You as well. Thank you very much.
Have a good night.
All right, you too.
Bye bye.
Bye bye.